Now, Galileo taught us that if you wanted to understand the universe, you had to measure it. Nowadays, we take a great deal of interest in the imperfections of the eye because we can measure them. And because we can measure them, there's an opportunity to try to maybe fix them.
Drawing on his electrical engineering background and quantitative skills, Larry Thibos has focused his research efforts on improving methods of monitoring and measuring visual performance and optical quality of the eye.
So what you're seeing here is, I think, the world's only two-dimensional scanning wavefront aberrometer. It was developed for the purpose of measuring optical aberrations of the eye, not only along the foveal line of sight, which is what most aberrometers do, but along multiple peripheral lines of sight. The patient sits right there, that's where the patient's eye goes. We have a beam of light now that is effectively rotating around the center of the eye's pupil. So if you can imagine a beam of light coming into my eye, we want to be able to rotate the beam around the center of the pupil, horizontally and vertically, with a central pivot point being the center of the pupil. And that's what these rotating mirrors do. It directs the beam in a different direction. So for the scanning wavefront aberrometer, the light comes into the pupil, at the center of the pupil, and it rotates at different angles. And as the light goes into the eye, then it hits the retina, and light gets reflected back out of the eye. And when the light gets reflected back out of the eye, it's captured by a lens-lit array to form an array of little spots, and the location of those spots tells us the aberrations of the eye. So I'm hoping that it'll be common practice in the future for optometrists to make a quick scan of a patient's eye and have on record the optical quality of that patient's eye over multiple lines of sight in a few seconds. In a way, we do clinical research here. Even though I'm not a clinician. And I can say that because I think that the things we learn help clinicians to better understand what it is they're doing. We've helped improve the quality of patient care by being able to better monitor the outcome of treatments that are applied to eyes. So I think the big clinical payoff in all this aberrometry is perhaps not so much measuring an eye so that you can build a better pair of spectacles or a better contact lens. My feeling is that the real clinical payoff is in the development of clinical ophthalmoscopes that make use of an aberrometer to measure in real time what the aberrations of the eye are so that you can correct them and do high-resolution imaging. That's where the payoff is.
In recognition of a remarkable career devoted to improving vision and eye care through experimental research, the American Academy of Optometry proudly presents the Charles F. Prentice Medal to Dr. Larry Thibos.
It is both an honor and a personal pleasure to introduce this year's Charles F. Prentice Medal recipient, Dr. Larry Thibos of Indiana University, who will now present his lecture entitled Wavefront Measurement of Refractive State. Please join me again in welcoming Dr. Thibos to the podium.
These microphones about right? Can you hear me back there? Okay, good. Well, it's a good day to be a Hoosier. I'm pleased to be up here representing Indiana University. There are quite a few Hoosiers on today's program. And I'm going to be telling you a little bit about wavefront measurement of refractive state. As you will all appreciate, no one in the modern world of research works alone, and that includes me. I've had the privilege of working at a university where there are many people of like mind. We have a large visual optics group at IU, and I can thank them all for their contributions in helping advance our program. I also have a large number of authors, co-authors to acknowledge. I was surprised myself when I started adding them all up. There are some 110 colleagues for whom I have had the privilege of working and published papers spanning some 11 nations and 40 years. In fact, there are so many I couldn't fit them all into one slide. Here's some more. We've also been very good in my lab at spending other people's money. So I want to thank you for your generous contribution to the National Institutes of Health, those of you who are American taxpayers, and for those of you from foreign countries helping to support your own international agencies that support scientific research. The National Institutes of Health has been very generous to me, supported my entire career at Indiana University, and I'm grateful for that. Well, as you can see from the list of countries here, that global vision research is a global enterprise these days, and I want to isolate and emphasize 3 individuals who helped me pursue my career. One of them is Professor Ray Applegate. Ray, unfortunately, couldn't be here. He's writing a grant for the National Institutes of Health, so he couldn't come. But Ray has taught me most of what I know about clinical optometry. And Ray has also been relentless in his demand that the work that we do be clinically relevant and have practical application. The other person I want to mention is Professor Arthur Bradley. Professor Bradley has an encyclopedic knowledge of vision science. He's taught me most of what I know about vision science. And he's also been an extremely loyal and colleague throughout my career at Indiana University, and a very good friend, as is Ray. And the third person I want to mention is my wife, Elspeth, who has taught me everything else that's worth knowing. In particular, she tells me that it turns out that not everybody thinks the way I do, and so I appreciate that she's been able to point that out to me from time to time. Now, our son, Cameron, is an avid New York Times reader. He's a former journalist, and he called me on the phone. He said, Dad, you won't believe this. Mom's got her picture on the New York Times. I said, well, send me the link. So I grabbed it just before the meeting, and sure enough, there was a breaking story about the red carpet affair that's going on here at the Academy. Now, some of you might not have been to the red carpet affair, but that's okay. I'll give you a quick update. The headlines reads, Thibos sweeps awards, goes home with both the Prentice and the babe. The text is worth reading too. It's short. Larry N. Thibos, mild-mannered professor at Indiana University, carried home the Academy's most prestigious prize today at the red carpet ceremony in Phoenix, Arizona. Thibos, of presbyopic age, said later that winning the prize was nice, but it didn't compare with winning the besilkened babe on the red carpet. And with typical Australian candor, Mrs. T said of her husband of 30-plus years, before he met me, the professor thought only wavefronts have curvature. Well, when the news about the Prentice Award reached the Midwest, I asked my students, do you know who Charles Prentice was? And they replied, well, of course. The man is known by his equation, delta equals C times F. Well, sensing a teaching moment in science history, I asked, well, then do you know who Albert Einstein is? And they said, well, of course. He's a square MC. Yeah, you get it. Einstein equals MC squared, right? And when I asked, well, why is your professor receiving the Prentice Medal? They answered, well, because 3 equations are better than 1. It's obvious. And when I asked, what does Prentice's rule have to do with wavefront refraction, their answer was, everything. What clever students we have at Indiana University. Prentice himself would have said the same. In his book, Ophthalmic Lenses, published the 2nd edition in 1907, he said, the prism diopter stands unchallenged in its unique ability to harmonize all of the refracting elements in an optometrical lens case by establishing a complete and inseparable relationship between prisms and lenses. Well, what is this complete and inseparable relation he was speaking of? And why is Prentice's rule even more important today than it was 100 years ago? Well, as every student of optometry knows, Prentice's rules tells us about how lenses refract rays. If we have a lens that is collecting light from a distant point source, like a star in the sky, that lens has a focal power of F, gives a focal length of 1 over the distance d, and all those rays get refracted by that lens and come to focus at point D, at the distance d from the lens. And so in Prentice's equation, the distance d is the focal length, the quantity c is the distance of any particular ray from the optical axis, and it's the product of c times f that tells us the angle that the ray makes when it strikes the optical axis. Well, there's another way of interpreting Prentice's rule that it's going to emphasize today, and that is if you were to draw a line tangent to the wave front of light, and the wavefront's defined as a surface perpendicular to all those rays. If you draw that little dotted line there, perpendicular to the ray and tangent to the wavefront, it makes the angle delta also, but not with the optical axis, with a reference axis that's perpendicular to the optical axis. And since the slope of the tangent is also the slope of the wavefront, what Prentice's equation is telling us is about the slope of the wavefront that's entering this pass through that optical lens. And that's a change in attitude that's very important. We're no longer talking about the lens itself, we're talking about the wavefront produced by the lens. Now moreover, this diagram shows you what a perfect wavefront is. Using Prentice's equation, if you rearrange things a little bit, if delta over C, if that ratio is constant, that means that all the rays have the same vergence. That means they all cross the optical axis at exactly the same point. And that is a perfect wavefront. Now, of course, none of us perfect, and that's true for lenses. Here's an aberrated lens, same light rays coming in, but notice that the rays don't intersect at a common point anymore. These are aberrated rays. In fact, this diagram is actually misleading in lots of ways. It's the kind of diagram you see in textbooks all the time. But some of those rays aren't even in the plane of the diagram. It's only our imagination that's in the plane of the diagram. Some of those rays come out of the diagram. They're called skewed rays. But nevertheless, we can draw a tangent line or a tangent plane to that surface for every ray and measure that angle delta. And that delta tells us about the slope of the wavefront at each point along the wavefront. And if we know the slope delta for many different ray locations, we can do a little bit of calculus and recover the shape of the wavefront as it's emerging from that lens. Well, here's an example of some of those rays that don't stay in the plane of the diagram, the uncooperative rays. It's an astigmatic wavefront. Notice the line perpendicular to this west astigmatic wavefront. It doesn't intersect the axis. It's skewed to the axis. Nevertheless, we can make use of those slope information to recover the shape of this wavefront, and in fact, any wavefront that's continuous. So what's it got to do with eyes? Well, instead of a light coming from a point source like a star in the sky, imagine that the light comes from an eyeball, where we've put a point source of light on the back of the eye, on the retina, and it reflects back out of the eye to produce a wavefront. And if we can measure the slope of the wavefront at numerous places along the wavefront, we have all the information that we need to be able to reconstruct that wavefront of light. Now, we might have thought we could do the same thing for measuring the vergence and ask, well, where do the rays cross the axis? But that's a little bit harder to do because the rays get all muddled when they cross the axis. They're all on top of each other. But if you back up and go in the other direction, get closer to the eye where the rays are still separate, you have an opportunity to measure the direction of individual rays as they propagate forward. Well, to be fair, Prentice was not the first guy to come up with this idea of isolating rays to find out where they go. In fact, the earliest reference I know is from more than 400 years ago. It got published in 1619, but Christoph Scheiner, a contemporary of Galileo and Kepler, had been working on this problem for a long time. And he described what optometrists know as the Scheiner's disk. It's a way of isolating a couple of rays of light to figure out what the refractive error of an eye is. And you'll remember also that Thomas Young, 200 years later, made use of that very principle to measure the astigmatism of the eye, the first person to do so. Well, people in other branches of optics might not know about Scheiner or might not know about Thomas Young. Well, they should know about Thomas Young. He was a very famous man. But they're more likely to know about a fellow by the name of Hartmann, who was a contemporary of Prentice. They were both in the early part of the 1900s. And Hartmann became well known in the optics industry because he devised a way to measure the optical quality of lenses and mirrors. And what was it? Well, it was a Scheiner's disk, but with lots of holes instead of just a couple. So that he could isolate many different rays at the same time, find out where they all go, and in that way measure the quality of an optical lens or a mirror. Well, a modern-day aberrometer makes use of one more invention by a pair of investigators right here in Arizona, not in Phoenix, but up in Tucson. Professor Roland Schack and his student Ben Platt thought that you could do a better job with Hartmann's screen if you replaced all those little holes with an array of lenslets because they'd be more efficient at collecting the light and focusing it down onto a sensor. So now you see a schematic diagram of a modern wavefront aberrometer. It uses a laser beam to put a spot of light onto the retina. When that light comes back out, it goes through an array of lenses, and each lens isolates a small portion of that beam of light, and depending on where that beam goes, we can figure out the slope of the wavefront. So although people call this a Shack-Hartman wavefront aberrometer, and you now will realize that the true lineage is a Shiner, Young, Hartman, Prentice, Shack, Liang aberrometer. Liang being the person who patented it about 15 years ago, 400 years after the basic idea was invented. Well, that aberrometer now gives us the opportunity to find out the shapes of wavefronts. And in optometry, for the last 100 years of its existence, I guess pretty much all of its existence, we've been concerned with just a few shapes of all the shapes that are possible. Those are the shapes of defocus that determines whether a person is myopic or hyperopic, and the shape of astigmatism, and perhaps a bit of prism. But that's 20th century optometry. What this wavefront aberrometer has done for us is make it possible to see lots of different kinds of shapes. Here's just two examples of trefoil, coma. In fact, there's a whole bunch of them. And they're known by the name of Zerniky Polynomials. Zerniky was very famous. He's a man who got the Nobel Prize for his invention of phase microscopy. He needed some good functions of this kind, so he invented them, and we still use them now. He donated them to vision science, and we use them to describe the aberrations of the eye. So the basic idea then is that if you can measure the aberration, the wavefront aberration map of a human eye, it can be thought of as the weighted sum of all these basic shapes. And only the ones above the red line have been used previously, and it's my prediction that people are going to be using the bottom, all those ones at the bottom more into the future. And in fact, this list is totally incomplete. It's a pyramid. It just gets bigger and bigger as you go further and further down the stack. Now, it also means that, of course, power vectors are passé. That's 20th century technology. M, J0, and J45. I think people will transition to talking about Zerniky coefficients. Well, that's a pretty heavy dose of optical theory. So early in the morning, I have to apologize for making you think so hard. So we'll just do a quick little fifth inning stretch here, the World Series time. On everybody's placemat, today you've got a piece of paper showing a bit of optical origami. Now the reason for that is that, as you've seen from some of these diagrams, optics is a very three-dimensional kind of problem to study, and the problem with most textbooks is they only draw two-dimensional diagrams. It seemed to me that what we need is the kind of textbook diagrams you used to have when you were a kid, and you open up the children's reading book and up pops Cinderella's castle. And so that's what this is. So if you fold it properly, in fact, I'll just give you a quick tour. I'm not going to spend a lot of time on this, but when it's folded out like that, if you fold it first so that you can't see the writing along the optical axis, you're onto it. And after that, you just follow your nose and the instructions that are on there, and you will have with you a Delta Wing high-performance aircraft, which at the point is the pupil center, and there's an optical axis going out at the bottom of the fuselage. There's a red spot on the back, on the top of the wing there. That's an object point, a point source of light in the object space. And the straight line from the object point to the middle of your pupil, that's called the chief ray. The plane connecting the chief ray to the optical axis is called the meridional plane, and that's what I've been referring to in my lecture so far. And perpendicular to that is the sagittal plane. So we have the meridional plane, the sagittal plane, and if you do it right, use a paper clip for the right amount of weight, you can get an airplane. All right, you win the prize. I wasn't sure it was going to fly. That's what I've done so far. Well, back to my story. When I look back in time as to when wavefront aberrometry, the concept of wavefront aberrometry changed our mindset, I picked 1997. And the reason for that is that was the year that Optometry and Vision Science published a feature issue that highlighted the work that was being done at that point in time using this new wavefront kind of concept for describing optical aberrations of the eye. And I think it's worth just reading that first paragraph about the new visual optics as an editorial that I wrote to introduce that feature issue. When I said that contemporary visual optics research is changing our mindset, our way of thinking about the optical system of the eye, and in the process is redefining the field of visual optics. All of the eye's optical imperfections will one day be represented comprehensively by a two-dimensional map in the plane of the pupil. This pupil map will look much like a corneal topographic map currently used to describe the shape of the corneal surface. But the interpretation of the two maps will be very different, because the pupil map describes how wavefronts entering the eye from each point in the visual world will become distorted from the perfect spherical shape needed to form the ideal retinal image. Well, I never would have believed that just 3 years later, that device that I was talking about, that dream of the future, had already arrived. Because in the year 2000, the first clinical wavefront aberrometer came on the market and made it possible to do wavefront-based refraction. We got one of the first units in Indiana. Is actually serial number 007. How does that James Bond thing? I forget how it goes now, but you get the picture. We had our own Bond girl in Indiana, Xu Cheng, who was a licensed medical practitioner from China, who became the first person to really make use of this in a clinical setting. And there's a change in mindset there, is that with an aberrometer like this, the process of doing wavefront refraction is to find the best spherocylindrical correction for the eye's defects. And at that point, we're no longer going to ignore the higher order aberrations. We're going to take them into account, and we're going to use them in prescribing the best possible corrective lens. And we do so under the basis of a key principle, and that principle is that the best prescription is the one that optimizes retinal image quality. That's what we want to achieve. But how can you access retinal image quality? I mean, the retinal image, think of it. The only person in the world who can see a retinal image is the patient. The clinician can't look inside and see the retinal image quality, so how are we going to know if we maximize image quality? Well, the answer is that we can calculate the retinal image. That was one of the reasons for measuring the aberrations in the first place. If we know the wavefront aberration accurately and with enough precision, we can compute the retinal image of any object using the principles of physical optics. The basic idea is you take a little bit of math, apply it to a wavefront error surface, and you can calculate the image for a point source of light. Well, that's just one point source, but any object in the world is just a collection of point sources, and they all get blurred the same way. So we can calculate the retinal image to say of an eye chart and find out what it looks like on the retina of your patient. And so for the first time, we actually can give the clinician some insight as to what their patient is dealing with when you keep asking this question, which is better, number one or number two? So the first question, of course, that we want to begin to deal with this aberrometer is to ask the question, where is the far point of an aberrated eye? And you see it's a bit tricky because it has aberration. So even in the case of simple spherical aberration, the paraxial rays come to a focus at a different place from the marginal rays. So if you put your letter chart in the plane where the paraxial rays are coming to focus, the image on the retina, we've discovered through these calculations, is sharper and clearer. That sounds familiar, right, for the practicing optometrist, sharper and clearer, but it has lower contrast. Compare that with putting the chart in the marginal focus, where the image is now darker and more contrast, but perhaps not as legible, not as sharp. So it's by studying these aberrations, we can begin to understand what's this meaning about sharper versus darker and clearer and all that. It's in the image, it's in the calculated retinal image. So this optometrist's persistent question, which is better, you see, you can have many possible answers depending upon the criterion that your patient is using in order to answer the question. For example, the subject might be using their own internal sense of aesthetics or a sense of beauty and say, that was the nicest retinal image I've ever seen. That's the lens I want. Or they may have some preconceived notions and expectations about what an eye chart ought to look like. And so it's a question of fidelity, perhaps, to them. But those are kind of internal sort of decisions that a person can make. It's hard to make those scientific. I think a better way to go about it is to ask about functional quality and base your judgment of quality on the visual performance of that patient. So the functional criteria, number 3 on this list, makes image quality measurable objectively, and that's the key. So we can elevate some of these ideas now to a lofty goal of establishing a psychophysical linking hypothesis. And that's a key principle in science, to be able to have a principle that relates the mind and perception of psyche to the physical world of observable events. And this is the principle that I offer, and that is that better performance indicates better images. And conversely, better images yield better performance. And with that rule in place, it becomes possible to do objective refraction. So here's a scientific paradigm now for evaluating image quality and deciding which is better, lens number 1 or lens number 2. We take that wavefront aberration map, calculate a point spread function, which itself is a description of the image, but we try to boil that down to a single number so we have an image quality calculator. One of our favorite ones we've investigated at Indiana is to basically look at for the strongest excitation of that point source. We weight it with a neural weighting factor and determine the brightest point in that image, and that's our measure. We call it the visual Strel ratio. So armed with a calculator like that, it becomes possible to do a virtual refraction. The goal here is the patient's looking at a chart, and we want to adjust a virtual lens to maximize the quality of the retinal image. So conceptually, it's like having a little mini optometrist inside the eye, peering at the retinal image and deciding if you've adjusted the lens just right to make the image as best it can be. But of course, we can't put a little optometrist inside the eye, but we do the next best thing. We measure the aberrations of the eye and calculate the retinal image and use our image quality calculator to reduce that to a number, and we maximize the number by adjusting the lens. And that should be the best prescription to provide for that aberrated eye. Well, it only takes one little step of imagination now, and you can see how to broaden the whole concept, not just measuring refractive error, but we're measuring the refractive state of an aberrated, accommodating eye. So here I've got an example for you to show you what it looks like to see a wavefront coming out of an eye as it accommodates. I chose a hyperopic eye so that we can have accommodate, relax, accommodate, relax. You see how the wavefront's changing? The main change in that wavefront is defocus, but the aberrations of the eye are changing too. In fact, I showed you this diagram a moment ago. That's for the relaxed eye. For most people, when you accommodate, the spherical aberration changes sign. So instead of the paraxial focus being further away from the eye, the paraxial focus is actually closer to the eye. That expands the range of accommodation, if you're using clearer and sharper as your criterion. So we wouldn't have been led to any of that kind of insight if we hadn't taken aberrations into account. So now we have a method for defining the refractive state of an accommodating eye. The patient's looking at a target, adjust the target any place you want, the eye accommodates, and the question is that target in the optimum location, or could we have gotten a better retinal image? Well, we trace our rays and say, no, guess what? We could have had a better retinal image if we put the target slightly differently. That indicates an accommodative error, and we can now measure that accommodative error using wavefront aberrometers. Well, this perspective now on accommodation issues opens up a whole bunch of new questions. For example, is the retinal image quality maximum for all states of accommodation? Or are we, as the textbooks say, all perpetual laggards, and we don't accommodate enough to improve the image quality to make it the best it could possibly be? That's an open question. How do changes in higher order aberrations and pupil size during accommodation affect refractive state? That's a rather radical idea. So a lot of people don't think the pupil has anything to do with refractive state. Refractive state is determined by the crystalline lens. But you take this wavefront perspective and all of a sudden the pupil becomes a player. How do age-related changes in accommodation affect image quality? For presbyopic individuals, we're very interested in that question. And do presbyopic therapies employing aberrations work? And if not, why not? Well, the clinical applications of wavefront methodologies are everywhere. I've only had a chance to talk briefly about automated refraction and objective measurement of the refractive state of an accommodating eye, but we're also using it to measure tear film optics and study the ocular surface. Wavefront aberrometry is an essential element in the high-resolution imaging being done with adaptive optics, because you have to measure the aberrations before you can correct them and do high-resolution imaging. Treatment strategies for correcting or even exploiting higher-order aberrations make use of this technology. And maybe it's even possible that the big-ticket item of myopia progression will become better understood when we understand the clinical conditions that control, the optical conditions that control ocular growth. Well, I want to finish on a more philosophical point here. I want to return to that editorial from 1997 and read the final paragraph of that editorial, in which I said that visual optics is the heart of optometry. But in the grand scheme of modern science, visual optics stands as the fourth branch of optics, the science of light and images. The other three branches of geometrical, physical, and quantum optics, they all deal with the physical issues of how light propagates, interacts with matter, and forms images independently of eyes or of vision. But visual optics, on the other hand, not only recognizes the role of the eye in vision and in optics, but it makes that role central. Thus, visual optics transforms traditional optics, which operates in the theoretical and physical domains, into the domain of human reality, the eye and visual perception. And it is through this transformation the science of visual optics makes its greatest contribution to mankind. For we are the ultimate consumers of images. Our eyes and brains give meaning to light. And in the same way, I believe that this Academy's mission should be stated as follows. By giving voice to the optometric research, this Academy makes its greatest contribution by way of the practitioner to the public's well-being. I thank you for the award. I thank you for being here to share it with me. And good day.
What a great presentations. Thank you, Dr. Thibos, for an exceptional presentation. We consider your participation in the awards program to be the highest honor for the Academy. At this time, Dr. Carla Zadnik will present Dr. Thibos with the Charles F. Prentice Medal.
She already did it. Yeah, and a big hug, too. Thanks very much.